Okay, today we're going to try to answer a very important question. What is energy? So let's start with sort of a simple example because that'll bring out a number of important points. So let's imagine we have a ball. Its mass is m, it's in a gravitational field g, and there's the ground. We'll say its height h off the ground. So this is a problem that you've probably worked many times in physics. So let's start with kind of the classic way you're probably taught to solve this by saying F is equal to ma. Now the forces acting on this object are just the forces due to gravity. So minus mg equals mass times acceleration, or the second derivative of the position. So x will be the position. So I can integrate this once, realizing instantly that the mass doesn't matter. So I get minus gt plus some constant of integration. And if I release the ball from rest so that time equals to 0, the velocity is 0, then my constant of integration is 0. I integrate again. I pick up another constant of integration. I get a 1/2 gt squared. And at time equals to 0, my position will be h. And I can rearrange this and say that at impact, when this thing hits the ground, the time, I just sort of solve that equation for when x is equal to 0. So when it's at the ground, I get the time and the velocity at that time, or dx dt at that time. If we simply substitute this value into here, we would get is equal to... Okay, so that's probably the way you were taught to solve this in physics. Another way to do this is to appeal to the concept of energy, which is probably something you've also a little bit familiar with. So if I wanted to solve this problem with energy, what I do is say, well, initially the object is at rest, but it's h units above the ground, so it has potential energy, mgh, and when it hits the ground at some later time, so right before it hits the ground, it has all kinetic energy and it's lost all its potential energy. Its kinetic energy would be 1/2 mv squared, where v is the velocity. And I just equate those for this time and the time right before impact. And I just equate mgh equals 1/2 mv squared. Again, the m's cancel, and I get the same result, that the velocity is the square root of 2gh. Okay, great. You're watching this video and you're like, great, I knew that already. But let's continue with some other things that you already know. So we have our formula that the velocity is equal to the square root of 2gh. So this tells us something, that as we increase the height, the velocity continues to increase, which might concern us because we probably have some concept of the idea of a terminal velocity, which our formula does not predict. So our formula does not predict terminal velocity. And the other thing is our formula predicts the velocity is independent of mass, but you know very well, if I take two objects, one being a ping pong ball and one being a rock, but of the same size, and I drop them, that the rock will fall faster and hit the ground first, which is not predicted by our formula. The velocity should be independent of mass. So how do we reconcile this? Well, you probably know the answer already, but if we did the experiment in a vacuum, these two would actually hit the ground at the same time. But we did the experiment in the room here, and so we did this in air. And as this falls, there's drag due to the air. So how do we account for that in terms of energy? Well, at a later time, our two objects have come to rest. So initially, we had all potential energy of mgh. Right before impact, we had kinetic energy of 1/2 mv squared. But as soon as it hits and comes to rest, where did all the energy go? Well, the energy went into not kinetic energy of the object, but kinetic energy of the air, which is kind of complicated to capture because it's swirling around. So we don't really quite have an easy way to sort of calculate that if we didn't know the initial potential energy. But we know the air is swirling around, and so it will have kinetic energy. So if we go back to our formula and we say, okay, well, we know that energy is conserved, and what that means is energy before equals energy after. And so before will be our initial state where we have only potential energy, mgh. And after will be the time just before impact. So the object has 1/2 mv squared, its kinetic energy. But I'm going to say plus, and I'm just going to say the energy of the air. So whatever energy we've imparted to the air, kinetic energy of it swirling around, is some number. We don't know what that is. So let's rearrange this formula and solve for V. So we get the formula we had before, 2gh minus whatever we've given to the air times 2 divided by m. So this is explains our result for the ping pong ball and the rock. So the mass of the ping pong ball is much, much less than the mass of the rock. So when it's the mass of the rock, the energy in the air gets divided by a larger number. Now, since the ping pong ball and the rock are the same size, we might suspect that the energy of the air might want to be comparable to, since the size is the same, but in the rock's case, it's divided by a larger number. So the energy that's given to the air is kind of a smaller fraction of the total energy that exists in the system. So it's the larger the mass, the closer we are to the ideal result. The smaller the mass, the more we depart. Okay, now you're really thinking, great, I also knew that. So let's tell you something else you already know. Let's ask the following question. So here's the ground. Here's our object. Initially have a potential energy of mgh. And then I'm going to drop the rock. I'm going to let it come to rest. So the final state, the kinetic energy of my object is 0. The potential energy is equal to 0. And in the last example, we said, well, the air is swirling around, so it would have all the potential energy that we initially gave the system at mgh. But let's let the air come to rest as well. So I can also, if I wait long enough, we know that the air will eventually come to rest. So we'd say the kinetic energy of the air would also equal to 0. So the initial energy was this. The final energy looks like it's 0. So where did that energy go? Well, it went into thermal energy. So the air is now hotter. So we've warmed the air up just a bit. It might be hard to measure, but in fact we have. And this is pretty common in frictional processes. We know that friction heats up. If I take my finger and I rub it quickly on the paper here, I can feel it getting warm. So friction tends to heat things up. So just like that, the initial energy that we had in the system, which was mgh, has now been turned into thermal energy, which is warmer air. And now this is an important point for one reason, because if you think about it, when I had this object in its initial state, I could in theory construct a machine. I could have taken some sort of elaborate system of pulleys here. I could have connected this to a string. I could have then attached that to some other weight where it's maybe a little bit lighter than this initial mass, so it's some mass less than m, and I could have dropped this weight. I could have removed all that potential energy, and I could have raised this weight up. So I could have built a machine. I could have built a machine to lift things up just by attaching a string over a pulley. I could have also attached this weight to like a little flywheel that generates a motor, spins the motor, and makes a light bulb come on. But in the initial state, I could have extracted useful work from this. In the final state, though, when I just drop the ball and I don't attach it to any machine, I just drop the ball and it hits the ground, and we have this air which is imperceptibly but somewhat hotter than it was before, but just maybe by a very tiny bit. I now have this little tiny bit of warm air, and I really can't extract any useful work from that. And so not all energy is equal. And now, of course, it's equal in the sense that there's some amount of energy, some number of joules here, there's some number of joules in the warm air, so it's equal in that sense. But not all energy is equal if you're a machine and you want to extract work. So here we had potential energy, which is useful for extracting work. Later we have just this tiny baby bit of thermal energy, which is not so useful for extracting work. Okay, now you're really thinking, great, this guy is boring me. So this is kind of a trivial example, but I wanted to go through it just to bring out a few important points. The first is that energy is conserved. The energy before some process equals the energy after that process is over. Energy can change form. In our example, we had potential energy going to kinetic energy, going to thermal energy. Another important point is that a simple analysis with energy can put an upper bound on a result. So in the example we did with the ball dropping, its velocity was equal to the square root of 2gh, but that was the most it could be. If there was any friction due to the air, we would get a velocity less than that. Another point is that when the observation does not agree with the simple analysis, it just means you have not accounted for all the energy. So in our example, we got this result that the velocity when we dropped the ball was square root of 2gh. However, when we did it in air, we found that the velocity did depend upon the mass, which didn't agree with our result, so we had to account for the energy going into the movement and the heating up of the air. Subtle point is that energy is relative, only change matters. So when we did the example with the potential energy, we had our little object. We said it was h units off the ground. And so we defined this point here as being the ground and when the height is equal to 0. However, maybe we're doing the experiment on the second story of our house, and we might want to say, well, let me define this h to be 0, the height of the ground. Well, you could do that, and it wouldn't change anything, because it's only the change from this point to this point that matters. There's no rhyme or reason we need to call this the point where potential energy equals to 0, this the point where potential energy equals to 0, or sea level to be where potential energy equals to 0, because it's only the change that matters. As we saw in the example, when we drop the ball and it comes to rest and everything comes still, all our initial potential energy has gone into heat. And so this is very common. We have a lossy process friction or viscosity, as we'll often have in our course. Those losses end up as being heat. And finally, we saw that not all energy is created equal, especially if you're building a machine, right? So we had this example where we had this initial potential energy, which could be used to extract work. We could run some machine off of it. But when we converted all that energy into just a little bit of thermal energy, we have no way of then extracting that energy for useful work. So if you want to extract energy for useful work, not all energy is equal. And you should note when you do these videos that sometimes it's hard to spell. Observation, not observation. So let's talk a little bit about thermal energy. So the first idea is that thermal energy is equivalent to mechanical work. This is not something that's obvious. It's something that we really attribute to a guy named James Joule, who the unit of energy is named after. And what Joule did was, over his career, was he did a number of kind of important experiments that were very carefully done. And they varied, but kind of a classic one that you'll often see in textbooks looks something like the following. So there's an insulating box of fluid, maybe air or water. There's a little paddle wheel attached to a shaft, which can spin, which is outside the object. And then he would do things like take a weight, and he would drop this weight. It would unwind this little wheel here, spin the rod, spin the wheel, and he would measure how hot this gets and equate that amount of temperature change to the amount of energy, or the work done as this object falls. And on his gravestone, Joule has the number 772.55, and what that means is 772.55 foot-pounds of mechanical work would take 1 pound of water and heat it by 1 degree F. This is the number that he came up with, what he thought was the best number, and it's very close to what today would be the modern number if you convert these weird units, because of course when we're in engineering and science we don't really use foot-pounds very often anymore. And so when we have thermal energy, a formula you've probably seen before, maybe we've even talked about, is that when we talk about the change in the thermal energy, we have a formula for counting that, and it's the mass times something called C, which is the heat capacity or the specific heat, times the change in temperature. So the mass would be measured in kilograms, the specific heat would be measured in joules per kilogram Kelvin, the temperature change would be measured in Kelvin, so we put all that together and we get the change in energy in joules. Let's think a little bit about what 1 joule of energy is. So joule is a kilogram meter squared over second squared, or a Newton times a meter. So in terms of kinetic energy, which you calculate as 1/2 mv squared, 1 kilogram going square root of 2 meters per second in velocity would give us 1 joule. In terms of potential energy, which you calculate as mgh, if we had a 1 kilogram object 10 centimeters off the ground, that would be 1 joule of potential energy. Thermal energy, which you calculate as mc times the temperature change, 1 gram of water increasing its temperature by 1/4 degree Celsius would be about 1 joule. So just to sort of talk a little about the equivalence of something like potential and thermal energy, sometimes it's useful to keep some simple numbers in mind. So let's imagine we have a 1 kilogram object and we extract all its potential energy from some height h. and we're going to use that to heat up something. So we'll not the air because we don't know the size of it, but we use it to heat up 1 kilogram of water. So we'll build some machine. So our before state is all the energy, is potential energy in a 1 kilogram object, and we're going to somehow by magic convert all that into thermal energy by heating up 1 kilogram of water. So that's going to have to equal mc delta T. So here we have a kilogram, here we have a kilogram. So when I equate these two things, the mass ends up canceling. Sorry, the mass, not the specific heat. So now I have G times H equaling mc delta T. So G, we'll say is 10 instead of 9.8 because I like 10, it's a better number. H will be something in meters, but we don't know what that is yet, equaling about 4,000 joules per kilogram Kelvin is the specific heat of water. You can look up the exact number, but I like to remember 4,000 just for sort of remembering round numbers. And then we have our delta T, we'll say is going to be 1 degree. So how high does this object have to be to heat up our object by 1 degree? So we can see we have 4,000 times 1, we have 10 over here. So we get a height of 400 meters, which is pretty high. So that's kind of remarkable, right? So if we take a 1 kilogram object, we drop it from nearly half a kilometer, and we extracted all that energy, we could heat up a kilogram of water 1 degree C. So it's important to remember this in flow problems, that kinetic energy, even if we have a large amount of kinetic energy, it might manifest itself as very small temperature changes because of specific heat of our objects is usually quite large. So we have 4,000 joules per kilogram per degree. So we haven't yet answered the question, what is energy? So let's think about something real quick. Three forms that we talked about a lot were potential, kinetic, and thermal energy, where we have these formulas that look like mgh, 1/2 mv squared, mct. And one thing you should notice about this is that all the forms of energy have some formula that allows us to calculate what the energy is. You should also notice that it's not quantized in chunks, right? Because the height can be anything you want, G can be anything you want. Even if we talk about mass and sort of subatomic particles, maybe they come in discrete amounts, but still the height can be any continuous number. So the energy is not quantized, and likewise the velocity can kind of be anything. So it's not like there's little bits. We have these formula, things aren't chunked up. And so what we really have with energy is not really anything at all. What we really have is that conservation of energy is nothing more than a formula and an accounting rule. So all our forms of energy, we have some formula for it. And when we sum them all up, we have to get that things balance out. So if we lose energy from one form, it goes into another. And so we really don't have anything here other than energy being sort of a mathematical thing or mathematical formula. The best explanation of this kind of deep understanding of energy or non-understanding of energy is in Feynman's Lectures on Physics, which is a very nice book if you don't have it. But here he's talking about what is energy, this exact question we're trying to answer. And what he says, there is a fact, or if you wish, a law, governing all natural phenomena that are known to date. There is no known exception to this law. It is exact so far as we know. The law is called conservation of energy. It states that there is a certain quantity, which we call energy, that does not change in the manifold changes which nature undergoes. That is a most abstract idea because it is a mathematical principle. It says that there is a numerical quantity which does not change when something happens. It is not a description of a mechanism or anything concrete. It is just a strange fact that we can calculate some number, and we finish watching nature go through her tricks and calculate the number again. It is the same. Then he goes on with an analogy, which I'll skip. Comes back later on the next page and says, what is the analogy to the conservation energy? The most remarkable aspect that must be abstracted is there are no blocks. So in the analogy, he talks about keeping the number of blocks that a child has constant. Take away the terms, and we find ourselves calculating more or less abstract things. The analogy has the following points. First, when we're calculating the energy, sometimes some of it leaves the system and goes away, and sometimes some comes in. In order to verify the conservation of energy, we must be careful that we have not put any in or taken any out. So this is just like when we talked about the energy of the falling object going from the kinetic energy of the object itself to the kinetic energy of the air. Second, the energy has a large number of different forms. There is a formula for each one, just like we discussed a second ago. These are gravitational, kinetic, heat, elastic, electrical, chemical, radiant, nuclear, and mass energy. If we total up the formulas for each of the contributions, it will not change except for energy going in or out. It is important to realize that in physics today, we have no knowledge of what energy is. We do not have a picture that energy comes in little blobs of a definite amount. It is not that way. However, there are formulas for calculating some numerical quantity, and we add it all together, it gives 28, in quotes. Always the same number. It is an abstract thing, and that it does not tell us the mechanism or the reasons for the various formulas.